Alright, let's now discuss the theory behind Inrush. Fair warning, this half of the lecture operates under the presumption you have a passing familiarity with three-phase AC circuit analysis, motor starters, and have a basic understanding of electromagnetic interaction. If you had trouble calculating Inrush in the previous examples, this half of the lecture is definitely off limits to you. Only the strongest, smartest, and sexiest among you may proceed. Assuming you're still with me, you will no doubt recall that motors are devices that consume electrical power and produce rotating mechanical power via different types of electromagnetic interaction. One of these interactions is explained using the left-hand motor rule, which specifies that a current-carrying wire inside a magnetic field will experience a resultant force. This is the effect that turns the rotor. The second interaction is explained using the right-hand generator rule, which specifies that a wire moving in a magnetic field will experience induced current in a direction counter to the initiating current. This is known as counter-electromotive force, or CEMF, which can be thought of as a variable voltage source in opposition to the applied voltage across a motor winding. Counter-electromotive force is proportional to speed. The faster the motor is spinning, the more counter-electromotive force is produced in opposition to applied voltage. This is the effect that explains Inrush. More appropriate, it is the lack of this effect that explains Inrush. A motor at rest is not producing counter-electromotive force, and upon closure of a full voltage starter, the winding experiences full voltage. Consider this simplified model of a squirrel cage induction motor winding consisting of several components. The first of which is a small variable resistance, which is meant to represent the losses inherent in a motor's operation. This can be resistance losses, core losses, sound losses, winding losses, bearing losses, or anything else that doesn't go towards usable power output. I'd like to say this component is small enough you could ignore it, but it isn't. Any power consumed by this component would be considered a loss. The second component is also a variable resistor, which is meant to represent the real power consumed by the winding. The third component is a variable inductor, which represents the reactive power consumed by the winding during operation. Both these components are representative of a motor's operational state on the speed-torque curve. At certain points, the reactive portion could be greater than the real portion, and at other points, the real portion could be greater than the reactive portion. We'll examine real and reactive power and efficiency of motors at different points in the speed-torque curve in other lectures. Finally, of direct importance to this particular lecture, the fourth component is a variable voltage source in opposition to applied voltage, and its magnitude is proportional to rotational speed, which represents the counter-electromotive force produced as a result of generator action while the motor is in operation. At rest, counter-electromotive force is zero. As the rotational speed increases, counter-electromotive force increases. By the way, this is a mathematical model only, an extremely simple one at best. Do not expect to take apart a motor and find a variable resistor, inductor, and power supply in series with the winding. These components are a simple way of explaining the electrical phenomenon of a motor in operation. For the purposes of this lecture, let's just lump the two resistor portions into one variable resistance. Let's examine how rotational speed and the resultant counter-electromotive force influence inrush current by way of an illustrated example. Consider a quarter horsepower rated motor designed to operate using light industrial 3-phase 120 volt line to neutral, 208 volt line to line 60 Hz AC in a Y configuration. When operated at the rated speed of 1700 RPM, this motor is known to draw 1 amp of current. For the purposes of this lecture, let's assume this motor's windings at rest can be modeled as a variable resistance component of 15 ohms, a reactive component of 13 ohms, and at rest, the winding produces no counter-electromotive force in opposition to applied voltage. The total impedance presented by each winding is a series combination of these elements with a value of roughly 19.8 ohms at an angle of 40.9 degrees. Upon closure of a full voltage starter, each winding would experience full voltage. An application of Ohm's law demonstrates each winding draws roughly 6 amps, lagging each phase by a relative 40.9 degrees. This is the inrush phenomenon. Each winding experiences full voltage because counter-electromotive force does not exist with the motor at rest. A massive surge of current occurs because nothing opposes full voltage. Luckily, this phenomenon is temporary. After the inrush phenomenon occurs, the motor accelerates to the no-load speed of, let's say, 1,770 RPM. While doing so, not only do the real and reactive components change, so too does the counter-electromotive force produced as a result of increased rotational speed. Let's say the winding at the no-load speed can be modeled as a variable resistive component of 27 ohms, a reactive component of 66 ohms, and at 1,770 RPM, the winding produces 70 volts of counter-electromotive force in opposition to applied voltage. The total impedance presented by each winding is a series combination of these elements with a value of roughly 71.3 ohms at an angle of 67.8 degrees. With 120 volts pushing in one direction and 70 volts in another, each winding would experience a 50 volt differential. An application of Ohm's law demonstrates each winding would draw roughly 701.2 milliamperes, lagging each phase by a relative 67.8 degrees. This is the current draws in the no-load condition, a point on the speed-torque curve where the speed is high but torque is zero. This results in an output of zero mechanical power. The no-load current may be specified as NLA, no load amperes, on a motor nameplate. Let's say the motor is put to work and experiences some oppositional torque as it is being put to use either lifting, pushing, pulling, or pulverizing something. At the rated condition, the motor produces 1 Newton meter of torque at 1,700 RPM. This is 185.3 watts of mechanical power, roughly equivalent to a quarter horsepower. At the rated condition, not only do the real and reactive components change, so too does the counter-electromotive force produced as a result of decreased rotational speed. Let's say the winding at the rated condition can be modeled as a variable resistant component of 41 ohms, a reactive component of 34 ohms, and at the reduced rated speed of 1,700 RPM, the winding produces only 67 volts of counter-electromotive force in opposition to applied voltage. The total impedance produced by each winding is a series combination of these elements, with a value of roughly 53.3 ohms at an angle of 39.7 degrees. With 120 volts pushing in one direction and 67 volts in another, each winding would experience a 53 volt differential. An application of Ohm's law demonstrates each winding draws 995 milliamperes, roughly 1 amps, lagging each phase by a relative 39.7 degrees. Current increased, not only because the real and reactive components change at the rated condition, but also because the winding experiences less counter-electromotive force at the lower rated speed. It is this same phenomenon that explains the increased current draw of increasingly overloaded motors. As rotational speed decreases, so too does the counter-electromotive force in opposition to applied voltage. As a result, the motor draws more current. In summary, the current drawn by a motor is reflective of not only the magnitude of the real and reactive components at that specific operating condition on the speed-torque curve, but also the amount of counter-electromotive force experienced at that rotational speed. At higher rotational speeds, the winding experiences more counter-electromotive force in opposition to applied voltage, at lower rotational speeds, less. At 0 RPM, the winding experiences no counter-electromotive force in opposition to applied voltage, and it is this phenomenon, above all others, that explains the intense but brief surge of current known as inrush. Alright, before I let you go, let's take a quick look at some graphs of motors experiencing inrush. Here's a plot of current in yellow and rotational speed in blue as a function of time for an unloaded motor experiencing the closure of a full voltage starter. You note the unloaded motor experiences a massive surge of current, which quickly tapers off as rotational speed increases. Once rotational speed stabilizes at the no-load speed of 1770 RPM, current draw stabilizes. After 30 or so cycles of 60 Hz AC, the inrush phenomenon is over. Now here's another plot of the same motor in a different scenario. In the first scenario, the motor was unloaded. In this second scenario, I'm using a dynamometer to apply a constant 1 Newton meter of oppositional torque to the motor. This is meant to simulate some static load the motor needs to move at the start, like a pump or a loaded conveyor belt. You'll note that the inrush phenomenon occurs for a longer period of time, on the order of 60 or so cycles of 60 Hz AC, twice as long as the unloaded condition. Once rotational speed eventually stabilizes at the rated speed of 1700 RPM, current draw stabilizes at the rated current draw. This is meant to imply that the starting condition of the motor can affect inrush magnitude and duration. It's this same phenomenon that also explains why motors overload when they're single-phased at standstill. If the rotating magnetic field is never established, the rotor doesn't move and no counter-electromotive force is produced, and as a result, the motor experiences a sustained inrush condition. Alright, that's about it for today. In summary, inrush, like college, is intense and painful, but thankfully it's brief. Don't burn out. It'll be over soon enough. In conclusion, this lecture examined inrush calculations using motor nameplate data and examined the electrical theory explaining inrush. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.